Hello students, in this video we'll prove the rank nullity theorem. Let's suppose that T maps V into W is a linear transformation between two vector spaces, finite dimensional of course. Otherwise, we need something called the Fredholm alternative dimensional vector spaces, V and W. Then, the dimension of the null space of T plus the dimension of the image of T is equal to the dimension of V. Okay, that's the rank nullity theorem. Okay, and what you'll oftentimes see is this as the what? You'll see this as the nullity of T plus the rank of T is equal to the dimension of V. So you'll see this written in multiple ways in different textbooks over here. Okay, and so for our perspective, what we're going to do is just for simplicity, we're going to set this to be equal to n over here. We're going to set the dimension of V to be equal to n since it's finite dimensional. And so let's prove this result over here. Okay, so how do we prove this result? And so of course, there's first one sort of simple reduction to make, right? The first reduction to make in this proof, if the dimension of the null space of T is equal to 0, then T is invertible and therefore has full rank. Okay, and in that case, we know that the result is true. Okay, so in other words, if the dimension of the null space is 0, then we get this for free, right? If it's not 0, if the dimension of the null space is not equal to 0, then we can find the basis of the null space, then let V1 through Vk be a basis of null space of T, right? Now, of course, this is a subspace. That's a subspace. Okay? And so I can extend, of course, here K is between 1 and n, right? So K is between 1 and n. And then what can we say? Well, then I can extend this basis to a basis of V, of all of V, right? And so what we'll do is we'll have the ordinary basis of the null space. The first K entries over here are going to be the basis of the null space, basis of null of T. And then I'll have other vectors over here. So let's put those other vectors in. Then I'll have Vk plus 1. That's the first vector I'll add in, all the way up to Vn over here. And those are the extension basis. Okay, so I extend the basis over there. And so now I claim that if I look at T of these extension bases, that's going to form a basis for the image, right? So now our claim is that T of Vk plus 1 through T of Vn is a basis of the image of T, which of course is just TV, okay? So to prove that claim, I have to prove two things. I have to prove that it spans and it's linearly independent. So let's do both. So here's the first part of the proof. Let's let W be in T of V, okay? That means that W is equal to T of little v for some little v in the set V, right? But this is a basis over here for V, so I can write V by the basis assumption as lambda 1 V1 plus lambda k Vk plus lambda k plus 1 Vk plus 1 plus lambda n Vn because I can write any element of my space V as a combination of these things. Now by linearity, what's this going to be? By linearity, this is going to be lambda 1 T of V1 plus lambda K T of Vk plus lambda K plus 1 T of Vk plus 1 all the way down to lambda N T of Vn over here, right? Great. And so what have we just shown over here? Now these things over here, these first K elements are elements of the kernel, right? That's the base of the kernel. So all those things are equal to 0 since they're in the kernel, right? That is a basis of the null space. So they're in the null space of that thing. So those first K terms go away. And we've just proven that any W over here is a linear combination of T of Vk plus 1 through T of Vn, which shows that the span of this set is going to be what? The span of this set is T of V. So hence we've just proven that the span of T of Vk plus 1 through T of Vn is T of the vector space V, the image, right? Image of V, image of T. Great. Now I have to prove that the set is linearly independent, right? So now the next phase is to do the following. Suppose sigma k plus 1 T of Vk plus 1 plus sigma n T of Vn is the 0 vector, right? This tells me, of course, that T by linearity of sigma k plus 1 Vk plus 1 plus sigma n Vn is equal to 0, right? By linearity. But this says that this is in the null space, right? So therefore, that element inside T is in the null space of T. So that tells me that sigma k plus 1 Vk plus 1 plus all the way down to sigma n Vn is a combination of a basis of the elements of the basis of the null space. So this can be written as sigma 1 V1 plus all the way down to sigma k Vk for some coefficients sigma 1 through sigma k, right? That sigma k is not a vector, obviously, so let's eliminate that vector symbol over there. There we go. Plus sigma k Vk. And now I have a non-trivial combination of V1 through Vn, which is a basis for the space. And since this is a basis, this implies that sigma 1 is equal to sigma 2 is equal to sigma k is equal to sigma k plus 1 is equal to sigma n, and they're all equal to 0. Since that set forms a basis, and now I have a combination of them equal to 0, right? And so that implies that this set is linearly independent. So T of Vk plus 1, T of Vn is linearly independent. And now we're in a position to prove our theorem over here. So in other words, we've just proven our claim that this is a basis over here. And how many elements are in this basis? There's n minus k elements over here in this basis. So there's n minus k elements over here, and there are k elements over here. So let's see what we get over here. So in other words, let's go back to our theorem. So in other words, we've just proven over here that the rank over here is n minus k, because there's n minus k elements over here. We've proved that by assumption the nullity is equal to k, so k plus n minus k is equal to k, and we've proven the rank nullity theorem in this case when the nullity is equal to k, and then the rank will have to be n minus k, where the dimension of V is equal to k. So it's important to realize that what happens is that you can take the basis of the null space of T and extend it to a basis of the entire space V, since the space V is assumed to be finite dimensional, right? And then what will happen is that the image of the things that are not in the null space of T will form a basis of the image of T, again, by the finite dimensional assumption. So this gives us a powerful invariant in terms of the nullity and the rank, and this will become a lot in further applications to help us understand properties when we concatenate different operators together. We're going to use this result frequently to get rank estimates and null space dimension of null space estimates on operators, which will enable us to do factorizations efficiently. Thank you very much.